Today we are going to learn how to solve a system of equations. So in the last few lessons we learned how to solve a linear equation and also set up some word problems with a linear equation to be able to solve those, right? So today we're going to learn what is a system of equation, what does a solution to a system look like, or what does it mean to be a solution to a system of equations, and also how to find it algebraically. So a system of linear equations is simply a list of more than one equation that's sort of being considered simultaneously. Now, in this class, we're only going to be looking at systems of two equations. So basically what's going to happen here is instead of having one equation with one variable that you're trying to find, where so far it's been like solve for x in this one equation. Here we're going to have two separate equations along with two separate variables. Typically, there'll be x and y, and to solve it will mean to find both the x coordinate and the y coordinate that satisfy both equations simultaneously. So, like for example, these first couple of questions are just asking whether or not that coordinate pair is a solution to the system. So we're just basically checking to see if that's the answer or not. So to check to see whether or not a point is actually an answer, all you have to do is just plug in the first number into x and the second number into y. Okay, and you're just basically checking to see if it gives you two true statements. If it might work for one and not the other, in that case it's not a solution. In order for it to be a solution, it has to satisfy both equations. So if I'm just testing 3, 1, I'm going to put in 3 for x and 1 for y and just rewrite these equations. So the first one would be like 3 plus 1 equals 4. And yeah, you can check that out in your calculator if you can't do that mentally, but hopefully you can get that. That's true, right? And then for the next one, we've got 2 times 3 minus 1, supposed to equal 3, but 2 times 3 is 6, and 6 minus 1 is 5. So this is not true, which means 3, 1 is not a solution. Now, approaching systems like this is actually pretty useful, particularly on the TSI exam where everything's multiple choice, because I'm going to show you like the traditional, like how do you actually solve these, but if it's multiple choice, you can always use those answer choices and just plug them into the equations to see which one works. So you can bypass the algebra if the question's set up that way. We will get into how to do it algebraically, but I just want to throw that out there that if all you kind of understand is like how to check to see if a solution works, you can still get some of those questions right. If it's like, what's the solution to the system? Here are your answer choices. You could just test the answer choices until you find the right one. Let's try the next one. We're going to plug in 1 into x and 3 into y. We'll test both equations here. So the first one will be 1 minus 3, and that is negative 2, so that checks out. And we'll test the second one. 2 times 1 plus 3. 2 times 1 is 2, plus 3 is 5. Okay, so that means that 1, 3 is the solution. So 1, 3 is the solution. So any questions about how to test a solution? Okay, now visually, we're only working with linear equations here for these types of problems. And so whenever you graph a linear equation, and graphing really isn't on the TSI, so you don't really need to know about like how to do the slope and all that. It's not really a big deal. But if you are thinking about these graphs visually, the point that is the solution is the point at which the two lines intersect with each other. A graph is just basically a big list of numbers that satisfy the equation. So like when you see the graph of a line representing a linear function, that line is really just a collection of points that if you were to plug them into the equation would give you a true statement. So the point of intersection between two lines is going to be your solution. So like if I have the graph and I say, okay, there's your system, those two equations, what's the solution? You're just simply going to identify what the point of intersection is. So in this case, this would be 2 comma negative 2. I didn't have to do any algebra if you've got that graph. Now, you won't always have the graph, but if you do, if they give you a question which gives you a graph of 2 lines, said what's the solution to the system, you really just make sure that you identify that point correctly. For number 4, we can see that we've got a solution right here, and that's at negative 1 comma negative 3. So graphically, the graphical approach is actually pretty effective as long as that point of intersection lines up on the grid. You might think of a situation where maybe that intersection is not perfectly on the grid, maybe it's a little off. And so, if the solution is something like 2.2 comma 4, it's going to be a little harder to tell based on the graph. But if it does intersect nicely like that, then it becomes very easy to find that point of intersection. Now, we're working with 2 equations with 2 variables, 2 lines if you're looking at the graph. There are a couple of different scenarios that could happen as far as how many solutions you might get. Now, most of the time, you're only going to get one solution. There's just going to be one point where the 2 lines cross. Okay, that means that the 2 lines intersect. Here's an example, that first one where you have just one solution, right? One point where they cross. But it is possible if you have 2 parallel lines that they never cross. And so it is possible to get no solutions or 0 solutions, meaning there is no coordinate x comma y that satisfies both. In other words, there's not a point that's on both of those lines because they're never going to intersect. The last kind of weird scenario is if you have 2 equations that are exactly the same. Let's say you have y equals 2x plus 5, and the next equation is y equals 2x plus 5. If you were to graph those, they would lie right on top of each other. And so every single point that's on the line would count as a point of intersection because it's just intersecting everywhere because they're just on top of each other. And so in that case, you would say there are infinitely many solutions because there would be infinitely many points where they, intersect might not be the best word to put there, but where they're touching each other. Okay. Now these terms, this term coincident, you don't really need to know that one, but that's just what it's called when you have lines that do that. But that's just kind of an overview of what a system is, what a solution to a system means, how to find it. But let's look at how to find it algebraically. This is really going to be kind of the meat of this lesson here. It's if I just give you 2 equations and I want to know what is the solution to that system, how do we find that algebraically? Okay, in other words, we are trying to find both an x coordinate and a y coordinate that satisfy both equations. Now, there's a few different methods for solving systems. Way back in Algebra 1, you might have learned of a few, but really the only one you need for the TSI is this method of substitution. Okay, so we're really just going to cover one method, and I think it's going to be the most common, and honestly, it's probably the most effective, and you can use it for any system. So the way that substitution works is you're going to attempt to combine the 2 equations into one equation. And the way you do that is by isolating a variable in one of the equations. And most of the time, you'll already have that set. If you look at this first system, number 5, you've got the y is isolated in one of the equations. For number 6, we've got a y isolated in an equation. For 7, we've got an x isolated in one of the equations. And for number 8, we've got y isolated actually in both of them. You only really need one. But as long as you have one of the variables totally by itself, you are going to substitute what that variable equals into the other equation. So for number 5, since y equals 2x plus 1, we can, and this is why it's called the method of substitution, we can substitute that 2x plus 1 into y in the other equation. All right, so if 2x plus 1 is y, then we can take that 2x plus 1 and replace y with that. So this 2x plus 1, we're going to put right there. And then you'll have just a single equation with a single variable. Okay, we'll have 2x plus 2 times y, but I'm not going to write y because I'm going to substitute that y with 2x plus 1 equals 8. And now we just have a single equation with a single variable that we can solve just like we did, a couple of days ago. So let's go through the motions here as far as how to solve this. First, we're going to use the distributive property. So we'll distribute the 2. And that'll give me 2x plus 2 times 2x would be 4x. 2 times 1 is 2. So first step is to use the distributive property. Then we're going to use combining like terms. And we really just have 2 like terms here. We've got the 2x and then the plus 4x. So we're going to combine these two. 2x plus 4x is 6x. So we have 6x plus 2 equals 8. And now we've got this down to a nice little 2-step equation where we'll use our properties of equality to isolate x. So subtract 2 on both sides. Gives me 6x equals 6. And then if I divide both sides by 6, I get x equals 1. Now, if you're working these too quickly, you might just think you're done. Oh, I can figure out what x is, box your answer, and move on. But you got to remember that we have actually 2 variables here. We have an x and a y. So it's not enough to just figure out what x is. That's only half the answer. We have to go back and figure out what y is. But usually the second variable is a little bit easier to find. And that's because we already have an equation where that variable is isolated. Right? We're going to take this x equals 1, and we are going to substitute it into x in the original equation. Because y is 2 times x plus 1. So if x is 1, that means y is 2 times 1 plus 1. And you can use a calculator here, and you can use a calculator on everything in this class. 2 times 1 is 2, plus 1 is 3. So now we have x, we have our y. That's all we need. That's our answer. It's going to be, and we're going to write it as a coordinate 1, 3. Any questions about any of those steps we took? This is probably going to be the most intense algebra we're going to do this year. There's just a lot of steps. So yeah, and it just takes practice. I mean, you just got to solve a bunch of them. You'll get better and better at it as you practice. So that's what we're going to do here. Well, let's look at number 6. So notice we've got the y isolated in the second equation. So that expression is what we're going to use to combine the 2 equations. We're going to take that x minus 3, which equals y. It says right there, that is y. And we're going to replace y in the other equation with that expression. So we're going to rewrite that first equation as 2x minus 5 times whatever y is, in this case x minus 3, equals 8. All right, see how we're replacing the y with that x minus 3. Oh, did I say that again? Oh, it's equal to 9. Why did I write 8 there? Good catch. I don't know why I wrote 8 there. Now, you do want to be a little careful with the distributive property here. Because it is minus 5, make sure that when you distribute this, you take that minus sign along with it. Okay, we are going to multiply negative 5 by both of those 2 terms. So we should have 2x minus 5x, and then negative 5 times negative 3 will be positive 15 equals 9. Now we can combine like terms. 2x minus 5x is negative 3x. And now we've got a little two-step equation there, so we can use our properties of equality. We'll start by subtracting 15 from both sides. And definitely use a calculator, especially when you start throwing in negatives. And so 9 minus 15 is going to be negative 6. So negative 3x equals negative 6. And then we're going to divide both sides by negative 3. Negative 6 divided by negative 3 will be positive 2. And so that's our x value. Now, just like with the last one, just like with all of these, when you have a system, you do have to find both values. So we've got our x, but now we need our y. So we're going to take that x and substitute it back into that equation that has the y isolated. Because it says y is x minus 3. Well, now we know what x is. So y is 2 minus 3, which is negative 1. Sorry about that. So we've got x equals 2 and y equals negative 1. So the way we're going to write our solution is as a coordinate. So we are trying to represent a coordinate on the coordinate plane, an x, y, a combination of x and y that work for both equations. So we'll write it as 2 comma negative 1. Any questions about number 6? All right. Well, I've just got 2 more for you. Number 7 says x equals 2y plus 4, and then 3x minus 8y equals 16. So this one has an x isolated rather than a y. That's fine. Just be careful that you're plugging it into the right variable. So we're going to take this 2y plus 4 and substitute it into x for the other equation, because that's what x equals. So now I can rewrite that equation. 3x, I don't want to write x, actually. 3 times 2y plus 4 minus 8y equals 16. And so what's a little different about this one is that we're actually going to be finding y first. It doesn't really matter which one you find first. It all just kind of depends how the system's initially set up. So that's fine. Don't be worried that we're going to get y first. But here we'll use the distributive property with this 3. 3 times 2y is 6y. 3 times 4 is 12. And we do have some like terms to combine. We've got 6y minus 8y, which is negative 2y. So negative 2y plus 12 equals 16. Now we use those properties of equality. Subtract 12 from both sides. And that gives me negative 2y equals 4. So it looks like we are going to get a negative number here for y. Dividing both sides by negative 2 will give me y equals negative 2. All right, so y is -2, but we still need x. So we're going to take that -2 and do one more substitution. We're going to substitute this back into that original equation that had x isolated right there, and just rewrite it, but fill in that -2 for y. So x is 2 times -2 plus 4. 2 times -2 would be -4, and -4 plus 4 is 0. So now we've got our y, we've got our x. Even though we found y first, we'll still write our solution as x comma y every time. So our answer here, our solution to the system, is 0, -2. We've got one last example to go through. And even though I feel like this type of example is like one of the easier ones, I think it can still confuse a lot of people because they're used to just kind of plugging in one equation to the other. And so when you have two equations where you see the same variable is isolated in both of them, you're still going to do that substitution move, but then you're going to have variables on both sides rather than all on the same side. So yeah, we're going to take that 3x minus 2, and it doesn't really matter like which one you substitute into the other one. Here I'm going to take this 3x minus 2 and plug that into y. Okay, because y is 3x minus 2. So if both equations have the variable isolated, effectively what you're going to do is just set them equal to each other. So here I'd have 3x minus 2 equals 3x plus 4. Now, when I go to solve for x here, something weird is going to happen, which is that when I subtract 3x, and we saw this back on the first day, sometimes this happens in an equation, all the variables are going to drop out because 3x minus 3x is 0 on both sides. So what we end up with here is -2 equals 4, which obviously is not true, right? -2 cannot equal 4. But we had sort of something that we were supposed to do when something like this comes up, where you end up with a false statement. That just means there are no solutions. There's just no solution here. In other words, there's no coordinate that satisfies both of those equations. And if you take a closer look at those equations, that kind of makes sense, because if you look back to these graphs we had before, the scenario where there is no solution is the one where the two lines are parallel. And if you look at those two equations, they both have the same slope, just different y-intercepts. So, and I'm not going to be asking you to graph this, but just to kind of illustrate the point here, one has a y-intercept of -2, slope of 3 is going to do something like that. The next one has a y-intercept of 4, but it also has a slope of 3, so it has the same rate of change. It's got the same slope. And that's sort of the key characteristic of parallel lines, is that they have the same slope. So if you ever notice that, we're like, hey, the slope's the same, but the y-intercepts are different, you hopefully recognize right away it's going to be no solution. But even if you try to solve it algebraically, you're going to get those variables to drop out and give you a false statement, right? -2 does not equal 4. I don't even like looking at it. It looks ugly there, like -2 equals 4. What's that? This is false. Okay, it's never true. And so that's how you solve systems of equations. So today we're going to stick with the abstract, just like straight up equations and solving for x and y. Next time we'll look at some word problems that might pop up on the TSI, where you have to set up two equations and make set them equal to each other or solve the system that way. Yeah, that's pretty much it for today.